Welcome, students, and once again we're going to talk about atomic structure, and we're going to kind of pick up where we left off from our first video. And our first video we dealt with some of the history behind the atom and how we kind of discovered or figured out what the structure of the atom is and the different parts of the atom. And up to this point, we said that, well, we learned a couple things from Dalton. We learned that atoms are what combine together to form compounds, and so you have atoms of different elements combined together to form compounds. We also understood that atoms are different sizes and different masses. And so an atom of oxygen is going to have a different size and different mass than an atom of hydrogen. So that all atoms are not the same. And then we expanded from there. We learned from Thomson, who we said came up with the plum pudding model, that there was a particle that could move and leave the atom, and that particle was negatively charged, and we called that the electron. And then we moved on to Rutherford, and we said that Rutherford was the next guy, and Rutherford discovered that there was a particle in the center of the atom, known as the nucleus. He named the center the nucleus, and that particle in the center was called the proton because it had a positive charge. And he also learned that the atom is mostly made up of empty space. So there's a big gap between the atom, or the nearest electron, and the nucleus. Matter of fact, in class we may demonstrate how much space would be in between the nucleus and an electron. And we also learned that there is a big gap between the size of an electron and the particles in the nucleus. The electrons are about 2,000 times smaller. And so far we have a nucleus that's made up of protons, which are positively charged, and around them on the outside you have these electrons. Now how all that works, they haven't completely sorted out yet, so we're going to continue with some more ideas. And the next guy we're going to get to here and discuss, and we kind of ran out of time last time to get to him, but it's James Chadwick. And Chadwick is going to take Rutherford's model of the atom, and he's going to modify it just slightly. And what Chadwick basically discovers is something key. And if you guys could take your periodic tables out right now, that would be awesome. And once you have your periodic tables, what I want you to do is start by looking at hydrogen, and particularly the atomic weight of hydrogen, and that should be, I believe it's in red there. And you'll notice that its value for its atomic weight is basically 1. What that is it's basically the average of the mass, and that makes up an atom. And basically what they calculate for making up the mass of an atom is what's in the nucleus. Okay, so up to this point in time, we know protons are in the nucleus. There's 1 proton for hydrogen. It has a mass of 1, and therefore, if you look, its atomic number is 1, its mass is 1, there's 1 proton. All works very nicely. Now, if you skip on over to helium, this is where there began to be a problem, and this is where they began to kind of notice something. Helium has 2 protons. Its atomic number is 2, so it has 2 protons, and yet its atomic mass is different. Okay, what is its atomic mass? It's 4, right? Basically, it's 4. And so it's double what it should be according to the Rutherford model. According to the Rutherford model, the only thing that should be there in the nucleus should be these protons. And yet there was more mass in the nucleus than could be accounted for by the protons. And if you look, like oxygen, there's 8. Its atomic number is 8. That means there's 8 protons, but its atomic mass is 16. So again, it's double what it should be. And so Chadwick came along and kind of began investigating, well, why is this? Where is this extra mass coming from? And basically what he figured out is that there's mass that could not be accounted for by in the atom by the number of protons, And he figured out there's another particle in there. There's a third particle in the nucleus, or a third particle in the atom that's located in the nucleus. And he named this particle the neutron because it was neutral. And that's why they had so much trouble finding it, because it was neutral. If you remember, they discovered the first two particles, the electron and proton, based off of their charge, because they either repelled or attracted magnetic fields or alpha particles. Well, this neutral particle didn't do any attraction or repulsion, and so it was difficult to find. And it was only because there was this extra mass that was found in these atoms that, hey, we can't account for this mass. Where's it coming from? They figured out there was a third particle, and this third particle had to be in the nucleus of the atom. And so now we have the three major particles, sometimes what are referred to as subatomic particles, in the atoms. So you have Thomson discovering the electron, you have Rutherford discovering the proton, and you have Chadwick discovering the neutron. And so now we have kind of a new concept. You have the positively charged protons and the neutral neutrons in the center and the nucleus, and they make up most of the mass of the atom. And then somewhere on the outside, you've got these electrons. And that's kind of the current model, until another guy comes along. And that next guy is a guy by the name of Niels Bohr. And he's a Danish physicist. And he's going to change things a little bit. And mostly what he's going to deal with are the electrons. And a lot of what we're going to deal with from here on out is going to be kind of, okay, what about the electrons? It's pretty certain that the protons and the neutrons are in the nucleus, they're in the center. That's not going to change or be modified a whole lot. So the next two models that we're going to talk about, both the Bohr model and one in class that we'll deal with a little bit later called the quantum model, which is kind of the current view of the atom, both deal with basically positions of electrons. Where are those electrons? You may want to note that the Bohr model is also called the planetary model of the atom at times. Probably in school at some point in time you've drawn a picture, or somebody drew a picture of an atom for you and it looks something like a solar system. That's the Bohr model. Even though it's not actually entirely accurate anymore, that would be kind of his version. And he used the science of spectroscopy to discover a new model of the atom. And what spectroscopy is, it's basically taking different elements or compounds and then looking through a spectroscope, and it breaks the energy that's given off, or the light that's given off. Usually this is done by taking like a wooden splint and soaking it in a solution of that element and then lighting it on fire, and then you look through a spectroscope and it breaks the visible light into the lines of the spectrum. And what he found was that each element had its own unique pattern, and kind of like a fingerprint of the spectrum. And so what he began to try to figure out is, well, why? Why do they have these unique patterns? Why are they not all the same? What's going on? What's causing the emission of the light spectrum? And he came up, as a result of his continual experiments, he came up with a new model of the atom. And what he discovered was these spectra lines were given off as electrons moved up and down what are called energy levels, or what he named the principal energy levels. And this is super important. So this is a key concept for you to understand, that no longer do you just have this mass of electrons on the outside, which is kind of what Rutherford and Chadwick kind of envisioned. Bohr is now saying, well, the electrons don't all exist in the same spot. They exist on different energy levels. So some of the electrons will be on energy level 1, some on energy level 2, 3, 4, so on and so forth. And so it ends up looking more like a solar system than anything else. And he discovered what's called the principal energy levels of an atom. And we'll figure out a little bit later, we'll go over in class, how do you determine the principal energy levels and how many electrons can be held on a principal energy level. We will go over that and cover that. One key thing, and this is super important that you remember this for the rest of the year. This is a super important concept. That is that he stated that electrons normally exist at the lowest energy level possible, and that is what we call ground state. In other words, electrons do not like to have energy. They will try to lose as much energy as possible. They will try to travel all the way down to that lowest energy level. The lowest is energy level 1, and then 2, and then 3, and then 4. Each one has a little bit, as you go out further, has a little bit more energy. The problem is, well, okay, then why don't they all exist at energy level 1 if they like to exist at ground state, or if they like to exist at the lowest energy level possible? Why aren't they all at energy level 1? Because energy level 1 can only hold so many. In this case, energy level 1 can only hold a maximum of 2 electrons. Once it has 2 electrons, it's full. It cannot hold any more. And so then what happens then is once it's full, well, now what's the lowest energy level possible? It's energy level 2. Once that one's full, then it's 3. So any energy level can be ground state if the ones before it are full. Okay, but that idea that electrons trying to always move to ground state is super important. That will play a huge role in why atoms bond, or what we call chemical reactions. What are electrons trying to do? They're trying to move to ground state. They're lazy. They like to lose energy. That's the idea there. So a couple examples of kind of how this works. If you look at this diagram here, you have the nucleus in the center there. That's your protons and your neutrons there. And then you have here, in this case, I've only drawn 3 energy levels. What would happen here? Here's you've got your electron, and it's existing at ground state, energy level 1, lowest energy level possible. In this case, we're saying we only have 1 electron. And what's going to happen is we're going to add some energy to it, and that energy may be maybe this is a piece of wood and we light it on fire. Maybe we run some electricity through it. Whatever it might be, somehow there's energy added through it. And there's all kinds of ways you can add energy to something, or something can absorb energy. And so what happens is the electron becomes excited. It's now gained energy, so it's going to move up through those energy levels. But it doesn't like to move up through the energy levels. It wants to have the least amount of energy possible. So as soon as it can, it's going to start losing that energy. So here's kind of a visual example. Here it goes. It's gaining energy. Up. It wants to lose that energy and come back down to ground state. And so let's kind of do that again so you can kind of visually see that. Here we go. It's gaining energy. Up. Doesn't want to lose that energy. And as it loses that energy, as it drops back down, it gives off that energy in the form of heat, light, a number of other possibilities that can be electricity, whatever it might be. That's what happens as that, and that's what Bohr was seeing, is as he was seeing the line spectra, those different wavelengths of light, what he was really seeing was were the electrons dropping back through their energy levels. One of the things you're going to have to do is figure out how many electrons can fit on an energy level. A little bit later we'll talk about, well, which electrons would be on which energy levels, and yeah, it gets a little more complicated than that, but we'll deal with that at a later time. Here's kind of just a quick example, and this will be the last thing that we show, here you have a situation, for example, here you have your nucleus of the atom. Here you have your energy level 1, and it has 2 electrons, and it's now full. So once it's full, you go and you put your energy level 2, and energy level 2 here has 8 electrons. And these 8 electrons here are now full and complete, and so energy level 2 can't hold anymore. So now we go to energy level 3. Energy level 3 can actually hold more than is drawn here, but we're going to say this is all the electrons that are possible for this given atom, and so it's complete, it's done. And so now ground state would be energy level 3. We could add some more to 3, but not to 2 or 1. That's kind of the idea behind what Bohr taught, and we'll go over a little bit more detail in class.